Okay, thank you, Shrikant and Nadeem, for inviting me and, of course, organizing the Wi-Fi Knowledge Summit. It's been a great experience listening to all the talks here. So my name is Rabin Patra from Tarana Wireless, a company that focuses on building end-to-end solutions for fixed wireless access for broadband in particular. So my talk here is not really going to be about Wi-Fi in particular. I'll take a slightly outside view and looking at the real-world challenges when we are trying to extend broadband to every home in this country and around the world, and look at some of the first principles in terms of what are the technology choices, right? Whether they are present in Wi-Fi or 5G or something new, especially what Tarana is interested in. So why broadband? Okay, so needless to say that high-speed internet is very important for all of us. I don't really need to emphasize on that in this day and age, especially since we're working from home now. However, the reality is that most of the world is not connected using high-speed internet, even if they have some access. So there is a big need and a big opportunity at the same time. So this is the problem that is really belongs to all of us. So what's the problem actually? So why can't we provide broadband to everybody immediately, right? So most of us in this room, in this conference right now, are probably have some kind of wireline access, right? Some kind of fiber or cable access. However, a lot of the world, especially in India, but even in the industrialized countries, is not connected. And the reasons are pretty well known. The cost of laying down fiber or any kind of cable infrastructure is pretty high. You have to dig roads, get right of way, and so on. It takes a lot of time. And another thing is maybe slightly more subtle is that there's a great lack of choice. It's because it's so difficult to put in wired infrastructure that often it is there is only one incumbent in the market. For example, here there was a storm last week and we didn't have broadband for 5 days. So that's because we just don't have any choice. There's only one vendor who will come and provide internet here, right? So that again points to a lot of opportunity here. And of course, the question is why not wireless, right? So of course, that is all of us are interested in that. Why not wireless? So the question here is, can wireless provide the similar kind of performance? And this type of wireless solution needs to be outdoors. And of course, the one advantage we have is that it can be fixed. So we don't have the challenges of mobility really. So it's fixed clients and fixed base stations, but needs to work outdoors, needs to work at reasonably long range, which we're talking about a few kilometers, maybe up to 10 or 15 kilometers if you're in rural areas, and needs to provide definitely high speed up to a gigabit. That's kind of where we want to set the standard to, and needs to be reliable as well. So the challenges here are more, of course, in terms of whether we can develop the right technology, whether we can engineer it, and whether the physics allows us to do it, and whether the economics can also be beneficial. So I'll go through that one by one, those kind of challenges one by one. So first option for any time you do want to install any wireless link outdoors is, can you get line of sight? That's best, because once you have line of sight, you can predict the performance, you can plan the network, you're not going to see any variations from changes in, at least less changes in weather or anything external. But that's hard. And these are two pictures from what we have actually seen. This is Pune, in fact, right? So whenever you're in the clutter, at a potential client location, you often see that it's very hard to get line of sight to anything out there, any base station which is nearby. Okay, so you either have obstructions in from the buildings, or you have you might have multiple buildings, or you have to cross tree lines or hill lines and so on. So it's really hard to get. So of course you can try to overcome this by saying that I want to get line of sight, especially if you're trying to do something with millimeter wave. So you will set up a tower or a pole. And this is actually me in a previous life trying to do that, and it's really hard. It's really hard because it takes more effort, and if you do it, you still have problems with pointing it and making sure it remains aligned over time, and then nothing else comes into the way. So this is really a challenge that cannot be easily overcome. So what about non-line of sight? Okay, so we'll say that let's just use let's not rely on line of sight. However, whenever you have any kind of a non-line of sight situation, you have all kinds of other effects, such as fading especially you have, and that comes in various kinds. Right? So you can have because of trees, because of multiple paths, and so on. And if you really look at it, if you use a ray tracing tool, as we have then at the top half here, you can see that this is Manhattan actually. So between two locations, you in fact have hundreds of rays. So it's a really a challenging problem, and that results in deep fades, both frequency dependent and time dependent. And if you're planning a network, as some of you might be aware of planning a wireless network, you need to have a really high fade margin to account for such changes, unpredictable changes that can happen, unless you design your technology and engineer it to handle it. A related point is that whenever you have outdoor wireless links, especially non-line of sight links, you have all kinds of things that can happen to it over time. So the weather might change, and you have to think about that. There could be foliage that could change over time, again based on the time of the year. There could be dynamic obstructions like cars and buses and all sorts of things, which would change the channel between the two endpoints. And that what does that imply? That you have to really you can't really train your system once. You have to adapt continuously and often very fast, and that puts a lot of constraints on the system and the processing. Uh, Next point is actually a little more subtle, but I think it's well known to the audience here, is that when you're trying to scale these type of networks across a region, you really have to think about frequency reuse. Okay, and that comes in, there are two aspects to that. First is the fact that frequency is still scarce, even especially when you're talking about outdoor broadband. If you take out millimeter wave out of the picture, because that often needs a lot of line of sight, we're talking about mid-band spectrum, which is 3 gigahertz to 6 gigahertz, and now, of course, 6 to 7 gigahertz as well, as we have discussed. In all these bands, spectrum availability is still pretty limited, especially if you're licensing frequency, especially if you're, let's say, using CBRS and you get a particular channel from the spectrum management system. This is in the US, but this might get extended to the 7 gigahertz band. You will not really have a lot of frequencies to play with, even at the end of the day, even if you add a gigahertz of spectrum. So what you're talking about is you want to maximize however much you can by reusing frequency in the network. And this picture shows that to a little extent. If you see the left-hand side picture, you have multiple cells, so multiple base stations. So here you can see that there are a lot of client locations, which are the small circles, that are within range of more than one cell. So if you happen to try full frequency reuse, which is really what your goal is, then you will see a significant signal quality degradation on all of those clients which are within the range of multiple cells. So again, you need to have techniques to deal with it. The second aspect is that if you want to do multi-user MIMO, this is a different variation of saying that you need to have frequency reuse, because you're trying to create multiple beams with different streams of data, all operating on the same frequency band. So this is a significant challenge also, because if you don't do this, then your spectral efficiency is very limited in frequency constrained situations. The next point is about again about real life deployment. So now, if you talk about unlicensed bands, which Wi-Fi, LTE, NR, and all of those operate in, then we are talking about situations where reliability of the broadband links would go down in the presence of other people who are using the network. So this is natural to some extent, because we are trying to use cheaper, which is essentially free spectrum, which is unlicensed spectrum, and there will be other people using the net. So what do you do with that, right? So if you don't do anything with that, or if you try to find techniques which are not operating at a fast enough scale, then you can see significant degradation in the reliability of the throughput and the performance you are providing to the user, and that would be a significant problem for broadband. So here we really have to think about techniques which can cancel interference in real time and actively cancel interference, and that's also from a technology point of view that needs new approaches. So what else? So I think I went through quite a few challenges, but there are a few others, okay, and which are slightly more subtle. So one is that you can, of course, you don't want to be in a situation where you're throwing a lot of computational power at these things, which is of course possible, and Massive MIMO is going in that direction, because that makes it harder to actually develop the hardware, to limit the cost and the power that you consume there, and to be able to install it outdoors. Remember that all of this needs to be outdoors, so you really want it to be passively cooled if possible. So that puts constraints on how you can power it. Using PoE is definitely desirable, and that is also forces us to look at new algorithms and new methods of optimizing performance here. We talked about this a little bit yesterday when performance testing, but testing these type of methods in a lab where it's repeatable is also very hard. So you have to be able to replicate all these conditions that we talked about, like dynamic channel adaptation, multipath, external interference. How do you do that is not so easy, because unless you do that and convince yourself it works in a repeatable situation, you can't convince customers as well. Finally, all of this implies development of new tools which can actually predict non-line of sight performance in these type of environments very well. Of course, tools for line of sight performance prediction are available and are plenty, but it's much harder to do that in real life outdoor environments. And not only that, you also want to be able to plan the network going forward, that where should we add capacity. So you want a centralized view of that, and you want a single platform which can use for provisioning the whole network, used for managing it, debugging what's going on, and even at this summit we have heard about efforts towards that, to trying to use machine learning for figuring out problems that might happen in a large network, which are really talking about millions of nodes. So what are the potential solutions? Okay, so I'll now go through that. So the first challenge we saw was non-line of sight, right? So here, what we really want is very sophisticated adaptive beamforming that works on both sides of the link. So and that is important, especially if you want to really maximize the range that is possible. And if you do this, you can actually get non-line of sight range, and we have seen this in real world about of in a city like Manhattan, where the obstructions, the level of multipath is the highest, of between 2 and 3 kilometers, and if you go to suburban and rural areas, it can go it'll go much higher as well. So there are multiple benefits to doing this, but the algorithmic challenges are quite different, because when you're talking about beamforming on both sides of the link, you have to make sure that the solution that you come up with is converges, that it is optimal in a network scale, not just for a particular link. And you have to use high order number of antennas on both sides. So I can see that a lot of some of the new efforts in Wi-Fi are also going towards this direction. And once you're able to achieve this, that you can get a system gain of about 27-30 dB, and you reduce the fade margin a lot. So that helps you in planning these networks quite a bit. So the related aspect is that any such technique that uses that has to deal with multipath has to have a very sophisticated multipath equalization. So here you can see very briefly what happens. The x-axis is frequency, right? So if you have multiple paths, you see a lot of deep fades in the signal level, and there are variations across the frequency band. So that implies that any beamforming really needs to be very narrow band. So you need to have a lot of beamformers running in parallel. It needs to be done in the digital domain, and it needs to be adaptive, and it has to be very fast, because all these fading changes over time, and of course frequency here. So if you're able to do that properly, then you can get a gain of 30 dB or more, and again, what that means is that the variation over time is very low, so less than 2 or 3 dB. So that makes it much easier to plan these networks. Otherwise, you have to, if you want to provide reliability, you have to put a lot higher fade margin. I mean, I'm talking about typical outdoor wireless link planning. So that's a huge advantage if your fade margin can be reduced by using multipath equalization and making it very adaptive and very fast, and by that I mean hundreds of thousands of times a second. Yeah. So this comes to the point of frequency reuse. So here, what we have seen is that is not just the beamforming which is important. It's also null forming which is important to get high spectral efficiency. So here's a very brief picture of why that is important. So on the left hand side, we see a base unit, which is let's say a base station, which is talking to two remote units, right? So if you only use beamforming, then the base station unit sends a beam towards remote unit 1 and a second beam towards remote unit 2. So here we are also trying to do multi-user beamforming, right? So however, what's more important is that when the base station sends a signal towards remote unit 1, it also needs to null out the signal that it's sending to remote unit 2, so that when remote unit 2 receives a signal, it is maximizing the ratio between its own signal and the signal it doesn't want, which is from the other remote unit. So in other words, what's really important is that to decode any signal at the remote unit, the ratio between the strength of the beam pointed towards you and the depth of the null which is pointed towards you for other units. That ratio is really important. In other words, to maximize the performance of this network is not only important to point beams, but also to increase the depth of the nulls, and that makes the system actually interference limited instead of noise limited. And that's really important to appreciate in a dense network deployment, that everything is interference limited. So null forming is really more important, and especially given that all sorts of regulatory constraints exist, we are not really trying to boost power here. We are trying to create precise nulls, and that almost gives us the same results of the signal to interference ratio, or maximizing the signal to interference ratio. So and again, this is null forming it's a lot harder to achieve in practice, because you have to have fully retrodirective beamforming, as we call it. So it's the technique to achieve it requires development of new algorithms. And if you do this, you kind of achieve something like this, where the beams pointed from the base station now can individually point to different units.
Rabin, can we wrap up?
Yeah. No, I think I was planning to take 25 minutes.
Okay, we somewhat close. Okay, so try and see if you can close up in 2-3 minutes.
Okay, can you tell me how much I've taken? How much time?
You have taken about 22 minutes now.
Okay, all right. Okay,
yeah.
Yeah. Okay, so one other aspect of these type of situations is that, and we have seen that in Wi-Fi as well, that once you use OFDMA, the scheduling of traffic and scheduling of resources needs to have a spatial dimension as well, and that again puts additional constraints on how you can design your algorithms for that, and that's also very important when you're trying to achieve high spectral efficiency. So I will not talk about this too much about cancelling external interference, but like I said before, really the goal is to actively detect interference from sources which are not controlled by you, and actively means that you have to detect it within a few 50 microseconds or a few 100 microseconds. And if you're able to do that, then you can, even in the presence of interference which is stronger than your signal of interest, which is shown here on the left hand side, you can still, you will be able to cancel it and decode your QAM cancellations. And since this changes over time, interference, outside interference sources don't persist. This again has to be really adaptive and really fast. So I'll skip over this slide, and I'll mainly talk about, try to summarize what we discussed in the previous slides, which is actually what is the full technology space and what are the constraints that drive those, right? I'll try to summarize those here. The requirement we started off with was we want beamforming, we want long range, and in the presence of multiple paths. So what does that mean? Is that we have to have multi-antenna processing on both sides of the link, and that means that we need to have digital beamforming, we need to have distributed, what we call as distributed MIMO, and distributed computation on both sides of the link. We talked about why we need deep nulls for that is for high spectral efficiency, and we talked about why we need to design all of this to work in to work with low cost and less expensive electronic components. What that implies is that we need to have a lot of we need to create symmetric antenna paths in the system between receive and transmit, and that implies that we need to have a number of algorithmic development for software calibration here, and this is really important, and we need to have a lot of processing done in the digital domain. We talked about why the channel can change dynamically because of changes in the weather, because of changes in the external environment. That means that we have to adapt very fast. That means that we have to beamform, the beamforming solutions have to be computed hundreds of times or thousands of times a second. We talked about why we need to cancel active external interference. And that implies that we need to have algorithms to detect interference sources which are outside control. So, this is a summary of the state of the art. In fact, and may not have too much time to go over this, but this is trying to understand where are the current set of technologies which are available in the market. How do they match against and some of these aspects? So, while Wi-Fi and 5G it's going towards faster adaptation, more multipath integration. There is not much ability to cancel asynchronous interference cancellation. There is not that much ability to have high spectral efficiency or really have long non-linear stuttering, because really the optimization for these technologies is based on mobility. So finally, of course, a lot of the techniques that that I discussed is something that we have tried out and have implemented in the real world. And this is a summary of like one such result that we have. So the bottom line is it is possible to implement this. It takes a lot of time for the R&D to figure out what are the real world implications of some of these things. So the summary is that if in a sector we have been easily able to achieve 25 bits per second per hertz. It's a single sector. So if we extend that 3-sector deployment, you can very easily get close to 80 or 100 bits per second per hertz. So that means that a single sector can have 2 gigabits of capacity. This is real world. Almost all the links are non-line of sight, anywhere between 1 and 3 kilometers, and there's some really long links as well, which is like a 15 kilometer link. It also shows that the installation can be very easy. All of this hardly require any alignment or pointing when we install this. So that's all I have about.
Sure. Shall we take some questions, Rabin, so that
yes.
we can just, yeah. So there are 3 questions. Joy Curry's question is, does it make sense to think of fixed broadband wireless backhaul in the context of rural areas only? Can we say that in most towns, wired backhaul is available? What are your comments?
So a couple of comments. Definitely, it is very attractive for rural areas, not just for backhaul, even for the access. In urban areas, while you are right that many places there is wired backhaul, which is getting there, but I mean, still, if you look at the numbers, a large proportion of the world is not connected, and not only in India, where it's some places really hard to get access and put in fiber, and for many reasons, for economic reasons, such as I know that like in some cities, the right of way of 1 kilometer of fiber is like a couple of crores of rupees. So it is possible in some places, not in other places, especially old cities. But if you look outside India, in the US, the coverage of wired backhaul is still very limited. And the second point I mentioned in the beginning is that really it's a lack of choice. So even if you have some kind of wired backhaul, you only have one. And that is actually a big opportunity. And this is not me saying it. There are a lot of people who want to enter the market. That's what they're seeing as an opportunity. Is that most people in the world don't have a choice, and that's why they often get forced for service. And this is where wireless system like this, although you may not say that this is what will be needed 20 years later, because eventually everybody will get fiber, but this type of solution you can deploy very fast. And that means that that is a big market advantage. You can enter a market very fast.
Next question is from Sheila. So the array gain we get using multiple antennas and beamforming, is it not limited by the client devices?
It is not limited by client. So yes, and I think I did mention that in one point, is that to get the full gain, you need to have beamforming done at the client as well, which means that you need to have an antenna array at the client as well, and you can afford to do that because you're talking about fixed wireless access. Right, so you're not talking about a client which goes in your pocket. So the answer is yes, if that's the question. That to get the full beamforming gain, adaptive gain from both ends of the link, you need to have array processing done on both sides, and this needs to be both transmit and receive array processing. In fact, the advantage of our algorithms that we have been looking at is that it's really very symmetric. So both sides are really doing the same thing. This is slightly different than how the 5G has evolved, where most of the computation is done on the base station, and I think that doesn't give you the full optimal performance.
This ties in well with the next question from Ganesan. Beamforming gain can be asymmetric between the uplink and downlink paths, especially if the number of antennas is different at both ends. How do you maintain the same SNR at both ends? In your experience, which one is better, TDD or FDD in terms of spectral efficiency?
Okay, so I'll ask the so the first question is yes. While the receive or transmit gain in particular can be different because the number of antennas could be different on the base station and client. But like I said, since you want network-wide capacity increase, we really want to have most of this processing to be very symmetric. So what we have seen is that you want to have similar gain on both sides of the link. However, once you achieve this adaptive and convergent beamforming, it actually doesn't really matter. You get the same kind of overall gain both in the uplink and downlink directions. However, note that transmit power restrictions could be different on both uplink and downlink, and there are many other constraints which could make the SNR different. But you have to use techniques like adaptive power control. And a whole lot of things I have not mentioned, and then and that's what will get you to the right ballpark. To the second question, TDD or FTD. So a lot of these techniques, right, where we are talking about convergent beamforming, they are best to done with TDD, because what you're really trying to use is the symmetric nature of the channel. So whenever you have FDD, it's not so easy to have a closed form beamforming solution because the uplink and downlink frequencies are different. So you can't learn anything. Let's say a client is there, if it's trying to receive something from the base station, you can't learn anything about the transmit channel by receiving something from the base station. So that's why we have seen that a TDD system is a lot more efficient, a lot more optimal.
Thanks. I have a last question to close up. So these wireless solutions with all the excellent design that you're coming up with, do you see a possibility that you will provide this integrated with a wired solution? Let's say, for example, when this work from home scenario, which makes us all critically depend on the broadband. Do you think there's a possibility that you will work with, let's say, a wired provider and provide some kind of an integrated solution which can give us, the assurance that, okay, one of them goes down, the other will take over, etc., etc. Do you see that coming into the market? Are you working on those lines?
We are not at this point, but it's a good angle to to think about. I think to answer your general question, to make it really usable for everybody, there are like parts of it that need to be added to what I have described, and we are working on sort of an end-to-end solution for that. Right. So one is, once it comes to your home, you still need to be able to get it inside your home. So this is the client as you can see in this picture here, will be outside your home. It's very much like a Tata Sky endpoint that you put in there, right? And it'll the difference is that you don't need to point it to a satellite; it'll find the base station on its own. So you still need to be able to provide internet access inside the home, and we are looking at how do we integrate that in so that it can be managed all together. And we just saw in the previous talk that managing this whole system together is very important, and all that we want to do it from a cloud platform. So I guess I'm not directly answering your question, but there is definitely possibility of integrating the clients that we have with a local Wi-Fi or local wired solution, so that can provide internal access as a backup to something else. That's a different aspect that can also be considered.
Sure. So one more question has popped up. I think we'll keep this as the last. Does your algorithm, this is from Sheila, does your algorithm also do something about the rate adaptation to take advantage of any dynamic channel variations?
Oh, yeah, definitely. So I think this comes under the purview of, like, what we talk about, a three-dimensional scheduler, right? So this is anything that is varying over time, which is you have variation over frequency and variation over time needs to be handled by the algorithm, and needs to be finally fed into how the resources are allocated between the different users, and you do that based on what's the most efficient use of the resources. You do that based on fairness, and based on the demand from each of the users. So not only rate adaptation, there's power control, rate adaptation. All these algorithms have to kind of work together to get the best out of wireless channels such as this.
Thanks, Rabin.
Okay, Shrikant, one last question.
Please go ahead.
So Rabin, are you also looking at using 6 gigahertz for this use case?
Yes. So I think that's why I was very interested in listening to the talks yesterday. We are interested in that, and I mean, so from a technology, an algorithmic point of view, it can very easily translate to 6 gigahertz. And of course, there's more frequency bands which are available there, so that alleviates some of the issues that we see in just in 5 gigahertz. But finally, I think we'll come down to the same situation where you have to deal with interference from other people who are using the band at the same time. So you have to still have active interference cancellation, and of course you have to deal with dynamically acquiring frequency from possibly a centralized database of some kind. But to answer your question, yes.
Thanks.
Thank you. So Rabin is also from Tarana Wireless, who's a sponsor. So we'd like to thank them.